looking at standard L4. Standard L4, I can find the right hand and left hand limits and use them to make functions continuous. We've sort of talked about continuity, but we need to dive into it a little bit more today. Continuity is an important concept in limits, and we not only have to be able to determine if something is continuous, we also have to be able to make something continuous and describe the discontinuity if it is there. Alright, so a function is continuous if the following conditions are met, and we're going to define it under here. First condition that has to be met is the graph is unbroken. Okay, so a piecewise function would not be considered automatically continuous. So the graph has to be unbroken. The function at the c value is defined. So that means there's no hole at that c value, which would go back to the graph is unbroken. The limit must exist as x approaches c. Okay, so wherever your c value is, the limit has to exist at that point. The limit as x approaches c of f of x has to equal f of c. What this means is direct substitution works. And the last part of something being continuous or not is that it must be a smooth curve or line. No jinkety kind of graph. If a function is continuous everywhere except at c, the function has a discontinuity at c. So if you have a graph and it's smooth curve everywhere except at one value, so it's not continuous completely because the function at c is undefined. So let's say there's a hole. Then we have some type of discontinuity. There's two different kinds of discontinuity that are mentioned that you need to know about. Removable discontinuity. Removable discontinuity means it's continuous. The graph, when I say it is continuous, I mean the graph is continuous at all points except one. What this means in the graph is that there's a hole. Okay, let me just make sure. Okay. Non-removable discontinuity means that the graph is broken. What this means is that you either have an asymptote or you have a piecewise function. So graph is broken, asymptote, or piecewise. The reason it's called removable or non-removable is because with a removable, if you can factor or use the conjugate to simplify then you might have a removable. Example being, if I was finding the limit as x approaches 2 of x squared minus 4 over x minus 2. This is a discontinuity because if I plug in 2, I get 0 on the bottom. So I know there's either a hole in the graph or an asymptote. I either have a removable or a non-removable. To figure out what discontinuity I have, I'm going to go ahead and try to factor. Okay, so when I factor, stuff cancels and I'm left with x plus 2. Well, now I can directly substitute and get 4. When that happens, when you remove or are able to cancel out the issue being what's on the bottom, and simplify it, and then you're able to find the limit, then you have a removable discontinuity. If we were to factor and nothing canceled, then you'd still have a non-removable discontinuity. You can't get rid of it or fix it or simplify it away. You're just stuck with it. Okay, so steps to discussing continuity. You're first going to, let me try a different step here. Yeah, we'll just start with that. All right, first thing, you're going to try to rewrite the function so it is continuous. So you're going to factor and cancel, use the conjugate, etc. So some of the techniques we've already been working with, try to rewrite it so that it is continuous. If the problem cancels out, then you have a removable discontinuity. If the problem, and when I put problem in quotations, what I mean usually is the denominator. Because usually the denominator is the one that's giving us issues. So if the problem does not cancel, you have a non-removable. Now graphically, this is what happens. A removable discontinuity gives you a hole. You still have a discontinuity, but it changes to a hole. A non-removable discontinuity is an asymptote. Okay, so we're going to look at some examples here to discuss the continuity. Alright, so for example 1 here, if we have this function f of x equals x squared minus 1 over x minus 1. Okay. If we were talking about continuity, we'd be looking for these 5 things. Graph is unbroken. Well, let's say this. If a function fails any one of these definitions, then it's not continuous. So we're going to go with the first one, figuring out if the graph is unbroken. Alright. Well, we're going to go ahead and graph this, but maybe we'll graph it afterward. Alright, so first of all, we can see that there's going to be a hole in the graph, at least at a value. It's either going to be a hole or it's going to be an asymptote at 1. Because if I plug in 1 here, I get 0 on the bottom. Excuse me. So I do know the graph is broken, meaning it's not continuous. But now we're going to talk about what's not continuous, at where, what kind is it, so forth and so on. So I'm going to go ahead and factor the top. And x minus 1's cancel. Now because they cancel and you're left with x plus 1, we have some stuff we can say about this. So we can say that the function is continuous, and I will say that when I ask you to discuss continuity, I do expect this little phrase here. The function is continuous everywhere, except at x equals 1. Okay, so you have to define the function continuity. So we say, okay, it's continuous everywhere except there's one problem. At 1, we have a discontinuity. And then you have to describe what kind of discontinuity it is. So at x equals 1, your function has a removable discontinuity. Now what this is going to look like in terms of a graph is it's going to be a line with a slope of 1 over 1 and a y-intercept of 1. But at x equals 1, where that would hit your graph, you're actually going to have a hole. So we would have a hole there, but it's going to be continuous everywhere else. Okay? Let's look at this function here. Tan x. Okay, now if I was to graph tangent of x, I might treat this as 2 pi. Tan of x is sine x over cosine x. And cosine is 0, because I can't have a function be 0. My unit circle here. You have 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay. So I'm going to graph this one first because it's going to be a little bit easier to talk about the continuity statement after I graph it. Tangent is going to have an asymptote in terms of the graph wherever cosine is 0. So cosine of 0 is at, if we're at 2 pi, it's going to be pi over 2 and 3 pi over 2. So I'm going to go ahead and divvy this up. This is pi, this is pi over 2, and this is 3 pi over 2. Okay, so at pi over 2, 3 pi over 2, I have an asymptote. Which means the rest of my graph is going to look like that. Alright, so we would say, okay, my function, is continuous everywhere except at x equals. Now, it's going to be x equals wherever it's a multiple of pi over 2. So it's going to start at pi over 2. We're going to do plus or minus. Now, from pi over 2 to 3 pi over 2, from this point to this point, that's a whole half a rotation. So we're going to have to add pi n. Okay, so this takes care of everywhere the asymptote would be. Pi over 2 plus pi gets me to 3 pi over 2. 3 pi over 2 plus pi gets you to 5 pi over 2, which will be another asymptote. And that pattern gets repeated over and over and over again. Okay, and then we'll say, okay, at x equals pi over 2 plus or minus pi n, because you have to tell me where it is discontinuous, if it is, and then at that discontinuity, what kind is it? So at that kind of discontinuity, f of x has a non-removable, because you can clearly see that they're asymptotes. So you wouldn't have a limit as x approaches pi over 2 from either side, because the graph's going to completely different directions. One's getting way huge in the positive area, and one's getting way negative in the other side of pi over 2. They're not approaching the same y value. Alright, there are times when, depending on the function, we'll have to look at right-hand and left-hand limits. I know we've already talked about this before, but we're going to look at a couple of examples where they apply directly to solving for the limits or solving for continuity. So we're going to start with this function. Okay. This is continuity on closed interval. If we were to graph this, I'm going to make my graph a little bit bigger. If we were to graph this, it would intersect at 1 and 1 and 1 this way. And if you graph this in your calculator, it would end up looking like a semicircle. Now, the conversation you have to have with continuity is the same conversation. You have to tell me where it's continuous, where it's not continuous, and then where it's not continuous, what's happening. What kind of, is it a non-removable or removable? So we would say that this function is continuous everywhere. Now, we have to give this a domain because obviously the graph doesn't exist at all past a certain point. So it goes from -1 to 1 and stops. So we're going to put that domain in here, -1 to 1. And it includes -1 and 1. So the function is continuous everywhere on -1 to 1. To make sure that it's actually continuous everywhere on there, we can see there's no breaks here. There's nothing funky that would be going on. But we do have to make sure that it exists at both those points, both those endpoints. So when you're looking at a closed interval, meaning like this one's going to go on forever and ever and ever in both directions and grow both ways, both directions. Here we stop. Like there's no more graph anywhere else. This is all we get. This is a closed interval. You need to check the endpoints. By evaluating the limits from left and right. Because for continuity, if the limits exist as x approaches c, then that's part of the conditions for being continuous. So we're kind of checking that part. You only have to do this really with closed intervals though. Okay, so the limit as x approaches 1 from the right. So it's approaching 1 from the right. Sorry, this should be -1 from the right. Going this way, there's no part of my graph there. Alright, so -1 from the right. Here's my function. I'm going to try direct substitution first. So I'm going to plug -1 in. -1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. And then you look at the limit as x approaches 1 from the left. So it's approaching from the left. Same type of deal. Can I directly substitute? Yes, I can, and I get 0. Now, these won't always be 0. These won't always be the same number. It just happens to work out this time. But whenever you have endpoints, your graph completely stops, you're working in a closed interval, you do have to check the endpoints. As long as these match, then you're good to go. And you can say that statement. If you don't double check, and one of these limits doesn't work out, so you have a hole instead of it being continuous there, then this original statement would not be correct. So you need to make sure you check the endpoint. We're going to walk through the steps to making a function continuous. I'm going to do example 4 with you, and then we're going to do example 5 together. You know what, actually, we're at 18 minutes. I'm going to pause. We're going to do this one all together tomorrow.